Good morning. Welcome back to another day of Math 8. I'm your host, Mr. Quilter. Today we're going to be talking about rotation patterns. As we talk about these rotation patterns, what we want to look at is applying the principles that we've been learning over the last several lessons. Specifically today, we're going to be talking about the rotational pattern around a center of rotation going a certain number of degrees and a certain direction. I like this because this is going to be practicing what we've been talking about with using precision of language. We'll have an opportunity to read a lot of that, and we will have a lot of opportunity to practice our motions. So here's in this first problem, it says, let's rotate this figure in a plane. By the end of today, the goal is that we have a better understanding of how to rotate 90 degrees, 180 degrees, 270 degrees, and then to have a better understanding of the consequences of those rotations. For instance, what things look like and how I know if I've performed a proper rotation. So with this isosceles triangle, what we're going to do is the patty paper is going to be our helpful piece today. We're going to go ahead and sketch our drawing here. Hopefully get a piece of paper that you can use to help you do this, because today is really important that we understand what our rotational values are. A couple of things that we can do with this to help with our 90 degrees is use straight edges. Something that we know as a straight line is perpendicular values. Just to help you to see this before we begin, this is a right triangle square. And when I set this in there, I want you to notice that this triangle is in fact a right triangle. That means that this angle right here is 90 degrees. And so this is a very helpful piece when we go to do rotations of 90 in increments or multiples of 90 degrees. So when we set this up, here's our first thing we're going to do. We're going to go ahead and do a rotation of 90 degrees clockwise around center B. When I go and set my pencil here, we're going to use B as our center. And that rotation of 90 degrees, what we see with this is that our 90 degree angle right here maintains or is preserved as 90 degrees. And so how do I know when I'm at 90 degrees? Well, I just need to follow the angle that's here. And from this line, snapping to this line is going to be 90 degrees. And that'll work every single time. From here, there's 90 degrees is my first one right here. And so I can simply just come here and just go ahead and write right over the top of my stuff. And I'll just put a little point right there where it was. And using straight edge is going to be really the ideal with this. Make it nice and pretty. Make sure we get a good looking figure. Now when I go ahead and do this, I come back to my original. It says go back to triangle ABC and now rotate 180 degrees. Well, we know 180 degrees is 90 times 2. So we're going to go ahead and rotate our 90. And then we'll rotate again another 90 degrees. And then you say, well, Mr. Quilter, we went off the paper. Yeah, we did a little bit. But that's going to be okay because we can work with that. Even though it's off the paper a little bit, the rotation still happened. So what we can do with this is we just draw best we can what we can represent on our paper or on the paper that we're given. And if you want to do this on a separate piece of paper, that's totally fine too. Or check this out. Take a line right across here and make a straight line. Because we saw that the top edge of this paper the top edge of this triangle came through here. And then if you have some kind of a 90 degree, since it's off the paper, we're going to try and see if we can get this just right. Use your straight edge underneath the edge or use another piece of paper under the edge that's an equivalent size. And then mark your triangle. Go back to the very beginning. And, perhaps what we should do with this, just to help us to see it, is we know that this one from here to here, we'll go ahead and label this as 90 degrees. We know the next one from here to here is 180 degrees. And then our third and final one is saying rotate 270 degrees clockwise. So let's go back here to the very beginning, rotate each time. 90 degrees for our first one. Apologize, my hand's in the way. Let's see if I can do this the other way. 90 degrees here. 180 degrees, so another 90. And then one more 90-degree angle to make 270 degrees. And what we see is we end up with a nice square that's going to be completing this figure. Go ahead and draw our line on there. And our last little vertex actually went off the page, but let's go ahead and write this arrow on there. Whoops, too far. Taking our angle from there to there, and we see this is a 270-degree angle. So what would it look like when you rotate your 4 triangles 90 degrees clockwise around B? Well, what we see is the rules of transformation that we talked about yesterday is that the lengths of segments are preserved and the angle measures are preserved, meaning that the lengths of the segments and the angle measures don't change. They simply stay the exact same measures every time I rotate it. So we see that each of these triangles are actually the exact same triangle, just copied after 90-degree rotation, a 180-degree rotation, and a 270-degree rotation. The next piece we look at is what happens when we rotate a line segment. In this case, if you want the interactive, here's the website you can go to at the top of your page. Just type that into your URL and you can go on there and play with it as a digital version. The idea that we're going to look at here is we're going to rotate segment CD 180 degrees around point D. So here's our center of rotation. Here is the shape that we're going to translate, or that we're going to rotate, is the figure, or is this line segment CD. We're going to draw its image and label its image, or label the image of C as A. So when we get this piece rotated, it's going to become A. Now, here we go. We have our line segment, point D, point G, point C, and we're going to rotate 180 degrees. Now the question might be, well, what is 180 degrees and how do I know what it is? As we saw in the previous problem, 180 degrees is half of a circle. This segment right here, 180 degrees away, continued in a straight line. So sometimes what we see as a 180 degree rotation creates a straight angle. So when I say straight angle, I'm talking about a straight segment or a straight line that has a vertex where everything is rotating around to create a straight line. So when I say straight angle, hopefully we know that straight angle means a 180 degree angle. Going back to our figure, we want to maintain this same pattern that we see right here, going up 1, rising 1, and running 2. So up 1, right 2, up 1, right 2. And we'll go ahead and rotate this around center D 180 degrees. You'll notice that they didn't say anything about the direction, and that's because it's kind of cool. 180 degrees does not matter about the direction, because either way, you end up with the exact same line or the exact same figure. So what we're going to do is we're going to go ahead and mark point G prime, and we're going to mark point C prime. We're going to recognize that D prime is there, but remember when we put C on here, we're not going to put C. We're actually going to mark this one as A. And this one right here, this will be G prime. And then the questions come around, well, what about D? If you rotated D, won't it be a little different? Yeah, we'll go ahead and put D prime there. Please use a straight edge whenever we do these on graph paper. If you're doing this digitally, make the straightest line that you possibly can. And there we go. We see that when we rotate a line or a segment 180 degrees around a fixed point that's part of that line, we see that found that segment just continues on in another straight segment following the same previous pattern. So what happens if we take that same segment and we change our center of rotation? We're going to go ahead and rotate around center E instead. Only this time when we draw its image, we're going to label the image of C as B and the image of D as F. So G prime, I guess that one got skipped over in here. We'll go ahead and call G as H, just so there's a good differentiation between them. So now we're going to take this off of our piece of our point E, and we're going to go ahead and rotate 180 degrees around point E. Now, how am I going to know where 180 degrees is? Well, thinking about what we did before, we know that 90 degrees is perpendicular to this line. So 180 degrees create a straight line. Let's go ahead and take this 180 degrees. And this is that first consequence that I was talking about with rotation. What we want to understand about this is that whenever I rotate, let's make sure I label these the right way. C becomes B, H, and we said D becomes F. Whenever we rotate a line or a line segment 180 degrees, the consequence of that is that we have a set of lines or segments that are parallel to each other. If I do a rotation of 180 degrees and lines or corresponding sides of a figure are not parallel to each other, then I did something wrong. That should be a warning to us. A 180 degree rotation always has a consequence of parallel lines. If we take a look at these pieces, we rotate segments DC or CD 180 degrees around its midpoint. Welcome to a new word, midpoint. Midpoint is the middle point of a line or segment. This principle is going to come in big as we go through our work. We've kind of talked about it here and there, but this is something that's a new vocab word for some. We can't forget about it as we're going to use it down the road. So when we look at this around its midpoint G, we're looking for the middle of segment CD. Here's G. Let's come back to our patty paper. And we're going to rotate 180 degrees around point G. Perpendicular is 90 degrees. Another 90 degrees. And we see, what is the image of C? Well, the image of C is right here. This is actually point D. And the image of D is point C. If we rotate our segment around that midpoint, all the line does is it rotates to its opposite direction. So if we had arrows on here, if we were pointing an arrow this way, that rotation of 180 degrees would just simply turn the arrow around to point the other direction. So what happens if you rotate a segment 180 degrees around a point? Well, if you're rotating around any of the points that are on your current line that you're rotating, we get the same line. Or essentially, if it's a line segment, obviously it might move a little bit right here, but we do get the line that's containing those points. It continues to be on that same line that's containing the points that are there, because lines go on forever, segments do not. If you rotate around a midpoint around a point that's off of the grid or off of the figure, then we get parallel lines. So we're going to say this: on the figure, we see a straight, actually we're going to use a different word. We're going to go and work this a little bit bigger. We see a segment or line that coincides. There's a new word for us. Coincides means fitting directly to or snapping to the old line. So coincides with the original shape. Off the line or off the figure, we see a parallel relationship. So keep that in mind. The consequences of a 180-degree rotation, if it's a point that's in the figure, we see another figure that coincides or matches directly with that other line or line segment, following the same slope as we see right here. If we do a rotation off of the figure, so a point that's off of the figure, such as E, we would see a parallel relationship. Now, one more thing to help us out. This wasn't really a part of the lesson, but it's something that I've enjoyed learning as I've gotten into higher levels of geometry, and something that I think will help us along the way. All 180-degree rotations have one common thing with their center rotation. When I rotated around center E, recall this, that point D and point F, they were the same point. So those corresponding points, D and F, correspond together. You'll notice that through that center of rotation, there's a straight line that includes all three of those points. That point in the middle, or when we see three or more points that line up together, is called collinear. C-O-L-L-I-N-E-A-R. Collinear is when three or more related points lie in a straight line. Whoops. When they lie in a straight line, we can see the same relationship as we look at these other points. Take a look at point G, the midpoint of the original segment, and point H, the segment here, and the center rotation E. We see that those three lie in a collinear pattern, a collinear relationship. Now, if you take a look at the last two, point C and point B, those ones are also related points or corresponding points. And when we look at those ones through that center rotation, we also see a collinear relationship. And the cool thing that I like about 180-degree rotations, if I don't know where that center is, I can find it by connecting the related points, or the corresponding points from the two figures. And they will always pass through one common middle point. So keep that in mind as we get going through the rest of this, and as we see through a couple more lessons as we get going. So here we go. Here are two line segments. Is it possible to rotate one line segment to the other? If so, find the center of such a rotation. Well, that came back a lot sooner than you probably thought it would. So as we're looking at this, is it possible? It sure is. And to do that, what we want to do is, like I said, take these points. It's really hard to see, but there's a point right here, and there's a point right here, and there's a point right here, and a point right here. Hopefully that's a little easier. Now, when we look at these and we take these two lines, is it possible? I think that segment, wow, that segment's about the same as the other one. It's just a little tiny bit longer. Is it possible to take this segment and find some way of rotating it to match this segment? And it certainly is, because I can see that they're the same line, or the same length. Here's the other thing I want to verify between this. I want to make sure that they're parallel. I want to see what kind of a pattern there is for rate of change. And I'm going to count these. There's 1, 2, 3, 4, 5 units up, and 1, 2, 3, 4, 5, 6, 7, 8, and 8 units to the right. Let's see if the same pattern exists in the other one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Since the pattern of rising up 5 units and running 8 units exists in both of them, and this relationship is equal, I can say that these two segments are parallel. Remember that one of the consequences of a 180-degree rotation is parallel lines or parallel segments. That tells me that these two figures, these two shapes, these two segments are parallel, which means, well, check this out. if I come between these two and think about the line that connects these two pieces, and I come back to these two and I think about the line that connects these two pieces, we should see one common point where these segments intersect. It's right here. What you'll notice about that point is this point is also the midpoint between related points. So if we called this one A and this one A prime, we see that a related point right here, let's call this one point B, is exactly in the middle between the two of those points, 3 units this way and 3 units this way. Now if we call this one right over here C and this one C prime, we see that the same relationship exists right here where that's the exact middle. Up 5 units and then over 1, 2, 3, 4, 5. The same relationship should exist on the other one. Up 1, 2, 3, 4, 5. To the right, 1, 2, 3, 4, 5. And since that same relationship exists both ways, we know for a fact that that is in the middle of C and C prime. Point B becomes our center of rotation to make one rotation map one line segment to the other. Whew. This has been a lot. You're doing great. Hang in there. We got just a little bit more. So here we go with a little bit more of a challenge. Now, as you look at this, you're probably looking at that saying, Mr. Quilter, how is this a challenge? Well, let's look at it first. It says you can see a rigid transformations, or you can use rigid transformations of a figure to make patterns. Here's a diagram built with 3 different transformations of triangle ABC. First, we see that there's a rigid transformation that takes triangle ABC to triangle CDE. And then we have another one that takes triangle ABC to triangle EFG. And then triangle ABC to triangle GHA. And when we look at these, you might be thinking right off the top that you've got a good idea. And I don't want to spoil it, but I want to tell you there's a lot of ways to explain how this could happen. Let's start out with drawing our triangle. Here is ABC. And there's one thing that I'm not going to talk about with this because I want to give you the opportunity. I'll tell you about it at the end. So our first thing is saying, well, how could I get triangle ABC to triangle CDE? Well, what I might be doing here, very first thing is maybe I want to translate so that figure or point B, we see the point B and point D are both 90-degree angles. Here's our short side, here's our long side, here's our hypotenuse. These are the legs. We see that point B and point D are corresponding points. So I'm going to go ahead and translate straight along that segment from B to D. And then I'm going to go ahead and do a rotation around center D 90 degrees clockwise. And I see that that triangle snaps right onto the other triangle. So a translation followed by a 90-degree rotation works for that. Perhaps you say, no, I think I'm going to go ahead and do a rotation first right here, do a 90-degree rotation around point B. And then I'm going to translate from B to D. And that will certainly work. A rigid transformation that would work for this one to the next one would be a transformation of translate D to F and then rotate 90 degrees clockwise. Oh my goodness, that's the exact same description that I just used a moment ago. So is it possible then, whoops, just kidding, not from there to there. We need to go from here to the other one. So for this one right here, how would I do this? Well, perhaps I could take a translation from B to D, and then a translation from B to F, and then I could go ahead and rotate around here. There's 90 degrees and 180 degrees around center F. Or maybe I recognize that right here from this one, that this figure right here is, well, maybe a reflection will work. Well, no, reflection didn't quite work right there across the line. Oh my goodness, you can't even see it. So there's a reflection across segment BC. That didn't quite work to get it there. But maybe if I do another reflection across an unknown line, that doesn't really work for us, an unknown line, because we can't describe it. So let's continue with the pattern of the lesson. Let's just say with our rotations, we're going to go ahead and let's rotate around this one. We see that it's over here, the opposite side. We found that 180 degrees was the same way with this one. And so I rotate 180 degrees around center B, translate to D, translate to F. Or maybe you're saying, Mr. Quilter, that's too much. Maybe I just want to translate from B straight down to F, and that would work too. Find the last one for describing the rigid motion that takes you from A, B, C, again from the original, down here to triangle AF or GHF, and give that a shot. Now here's the challenge. Leave me a comment in the video there on YouTube that tells me what did I miss. It has to do with the center of rotation, where I could do each of these with just one rigid motion, taking triangle ABC to triangle CDE. It's going to require that you tell me about one more point that is not labeled on the plane. So you're going to have to figure out where is that center point that I could just rotate everything around. And here's the evidence that works with it. Do segments A, C, CE, EG, and GA all have the same length? Talking about these guys right here. Is the length of this segment right here the same as this segment here, the same as this segment here, and this segment here? Well, based on what we just did and the properties of rigid transformation, if this figure is equal to this figure, then I know that hypotenuse AC is equal to hypotenuse CE. And as we did the rotations, we saw that each of these hypotenuse or hypotenae all came out to be the same length. So definitely they are the same length. And our explanation is rigid transformations preserve lengths of segments. I'm going to write that down. Rigid transformations preserve. There's our hot word right there. Preserve means keep the same length of segments. In this case, our length of our segment was the hypotenuse inside of each of these. Okay, don't forget to take that little challenge. Leave me a comment below in the sections on the video. To recap with our lesson, what we want to see with this is when we apply a 180-degree rotation to a line segment, there are several possible outcomes. First off, the segment might map to itself, meaning that the segment will just snap back right to the original where it was at the very beginning. We can see that from the very first problem that we did. Excuse me. From this problem right here, that if we rotate around center G, it snaps back to its line or maps back onto segment CD, where D came here and C was here. Or we see that rotating around point D just produced a longer line segment that continued the pattern of the line segment. The image of the segment maybe overlaps with the segment and lies in the same line. So we would call this one overlapping. We also had that one word that talks about overlapping where it adds on or right on top as coincide. So we're going to add that one in here. Coincide. Whoops. Seems like it should be an S, but where it coincides with it. And then finally, the image of the segment does not overlap with the segment if the center is not on there, right? So if the center is not on the segment, then our consequence that we saw there was parallel lines or segments. We can also build patterns by rotating the shapes. For example, triangle ABC shown here has a measure. So this little M right here talks about measure of angle A is 60 degrees. If we rotate triangle ABC 60 degrees, 120 degrees, 180 degrees, 240 degrees, and 300 degrees clockwise, we can build a hexagon. It would be the exact same thing if we went counterclockwise, but the important thing to remember is that we're working in intervals of 60 degrees, and this is just an isometric plane. You've been very patient, and I didn't give you any breaks today to pause the video or anything. So I really appreciate you hanging in there, watching the video the whole time, listening to me talk so much. I hope that you're gaining things out of these videos. I hope that it's helpful, and I hope that I'm getting better at what I'm doing. So please give me feedback on what I can do different. Please ask your questions about the lessons and how to do things. Homework video will come shortly behind this video. I do appreciate what you're doing, and I wish you good luck today and everything that you do. Take care and work hard. Don't you dare give up.